So good evening. So am I audible?
Yes, sir.
Yeah. Thank you so much. So let's wait for a bit. Let some more students join, and then we can continue. So yeah. Uh, s- so Vishnu and Pradeep, uh, like I guess some students will join accordingly after some time, but like since nobody has joined till now, like if you have any doubts regarding the week 3 topics, so you can ask. Like if you have any doubts regarding from these topics, so I'm free to answer. Like, if you have any doubts regarding these three topics, like that has been discussed in week 3, or anything regarding the lectures of Professor Chakraborty from the NPTEL portal. So, yeah. You can either unmute yourself and speak up, or like you can just write your doubts in the chat box.
No doubt for there's no doubt.
Oh, okay. Thank you, Vishnu. No problem. Okay. So, Pradeep, you also don't have any doubt? Yes.
No, sir.
Okay. So that's fine. Okay. Okay then. Like if there's not any doubt and like students are not joining, then I guess we can just go ahead with the today's schedule and just speak up and solve some problems. So rather than just solving the problems myself, it would be really great if you two like help me out in like these concepts, and since you don't have any doubts, so any one of you, if you don't mind, like any one of you please explain me like what's surface tension. Like I don't need the proper definition, I just need like what do you understand by surface tension, basic understanding of surface tension. Vishnu, Pradeep. Like
The force which is acting on the surface of the fluid, it's called surface tension.
Force acting on a surface of a fluid. Yeah, that's right. That's correct. But like, could you please make us understand with some example, like, so that we can understand like where surface tension actually acts, like where it actually. You are absolutely right, but like, any example, any phenomenon where you observe surface tension acting. So,
for example, a ball which is floating on a liquid.
okay. Ball.
There is some surface tension. Surface tension will push the ball outward from the liquid. Those kind of forces is called a surface tension.
Yeah. So yeah, thank you, Pradeep. Thank you for your example. That's fine. That's absolutely correct. So thank you. Okay.
This is correct, right? To a fluid is that you are placing some ball over the fluid. The fluid will put some force towards the ball. Those kind of forces, surface tension.
Yeah. Thank you, Pradeep. I got it. Yes, it's great. Thank you. So, like as Pradeep rightly explained, surface tension is actually a force acting at the interface of a liquid, where, in a sense that, like for any substance, say a bubble in a scenario. So you can follow this diagram. So say this is a container and there is a liquid, and in this scenario we will have an interface of vapor, say air here in the air, in this case we can say vapor and liquid. So this blue line, that's the surface of the liquid, acts as an interface between the vapor and the liquid state. So if we, in this case, if we have a bubble, say a bubble floating on the surface of the liquid, here the bubble experiences different magnitude of forces because of the different states of liquid available in this container. Say the vapor exerts different kind of force and the liquid exerts different kind of force, but still the bubble tends to have its integrity, like the bubble tends to remain in a circular shape rather than breaking down and mixing with the liquid. So the force that the bubble exerts to keep its shape is a per unit length, say the diameter of the bubble, is known as surface tension. So there's the basic definition, and you both of you, like, I guess, absolutely clear about it. So that's absolutely correct. And the energy, or say it is I explained it in terms of force, but if you want to say in terms of energy, like the energy required by the bubble to keep its shape in the liquid surface, then that type of energy is known as the surface energy. So that's fine. And basically we denote surface tension as sigma, and but we might have different notations in different books, but for our current course, like Professor Chakraborty has used, so I will also use the same notation. So surface tension is denoted by sigma, which would be force per unit length, and here length is the length along which the surface tension force is acting upon. So in this case for the bubble, the length would be equal to the diameter of the bubble. And say if we have, say, a concentric geometry, say I have two, say interface in such a way that there are two bubbles, one inner bubble and one outer bubble. So in this case, could anyone, both of you, one of you, please explain what would be the, say, I will just mention what would be the length that we need to use to find the surface tension. Say it is Ri and this is Ro. So in this case, could you please explain what will be the length? Say F is the force that is required, surface tension force is required to remain to keep the integrity of the bubble. So in this case, what will be the length along which the surface tension force is acting? Yeah, please. Pradeep.
We need to calculate for both bubbles, right? Separately for first Ri and for the next one R2.
Ro, yeah, absolutely correct. So in this case, it would be the diameters of, circumference of both the circles. So that be given by pi
D.
Yeah, pi do plus pi di. Yeah, absolutely correct. So just to have a clear concept here, yeah, right? So this would be the length along which the surface tension force will act. Okay, I feel the basic concept of surface tension is absolutely clear. So one of such phenomenon, like the most common phenomenon where we observe surface tension acting is the capillary rise. So capillary rise is a very important phenomena for life. Like you can, as you know, this is a phenomena by which the nutrients from the soil is being absorbed by the roots of the plants. So, and also, like if you have done your so if any one of you have done experiments of capillary rise in your class 11 or 12, you would have observed that you will be asked to place a thin glass tube, very thin glass tube in a liquid surface, and you'll observe the rise in the level of water within the thin glass tube. So if there's a thin glass tube, say given by this, there's a thin glass tube. So once you put the thin glass tube in the liquid, you will see a rise in the level of the liquid. Say it is given by H. So this is basically known as capillary rise. So if you have attended the lectures, I guess you will know the expression for this case. Say if it is water, the expression for capillary rise will be given by H is equal to 2 sigma cos theta by rho g r, and say r is the radius of the glass tube. So it's like that, and cos theta is the angle of contact. So I guess these things are like clear for all of you since you mentioned, and since Priyanka recently joined. So Priyanka, like, do you have any doubts regarding the three topics that have been taught in week 3 of the Introduction to Fluid Mechanics course: surface tension, fluid statics, and manometers?
No, sir.
Oh, thank you. So I guess you are well aware of this expression for capillary rise. And similarly, if say I ask you, one of you, to tell me, like, if the instead of water the liquid is, say, now mercury, if it's mercury, what will be the expression for capillary rise in this case?
The angle of contact will vary.
Yeah, thank you. Yeah, angle of contact will vary. So instead of say, I will just zoom out this picture. So if I, for in the case of water, the meniscus formed is some is of some this shape. So the angle of contact in this case becomes, say, if we extend it, the angle of contact becomes this becomes a theta. This is for water. But in the case of mercury, the meniscus is just oppositely shaped, like it is concave in this case, so it will have a convex shaped meniscus. Since it is hydrophobic, so this will tend to have a different shaped meniscus, just opposite to what water has. So it will have meniscus of this shape, if I'm not wrong. And then the angle of contact in this case becomes, it is this, I suppose. So because of the choice of our is there anything, Vishnu, you want to?
130.
Yeah,
134 is it?
yeah, thank you, like, absolutely correct. So 125, which is a, I must say exact value, but yeah, you're absolutely correct. But in general, like, if the angle is not explicitly mentioned in the problem, so you could just, the expression for capillary rise in the case of hydrophobic liquids is basically given by 2 sigma cos 180 minus theta divided by rho, say whatever liquid it is. So in this case I told it is mercury, so rho Hg minus rho water into G and R is the radius of the tube. Okay, so I guess these concepts are clear. And so, like, if you just recall from your lectures, like if you attended the lectures, so could anyone tell me, like, what are the parameters upon which this capillary rise depends?
Based on atmospheric pressure and the density of the liquid.
Okay, one by one. Pressure, then
Density of the liquid.
okay, yeah, then there are many.
Geometry of capillary tube.
Yeah, absolutely. Geometry basically means the radius. In this case, so like, so it is the radius. And anything else?
The material.
Material, okay, yes. So what is the parameter that the material of the, specifically the material of the tube decides, like?
Contact angle.
Okay. Contact angle, I guess the contact angle is because of the liquid used, not the material, but something else. Material, like, basically signifies the surface roughness, like, okay. So depending upon the type of material used, the surface roughness may vary with material to material, and the capillary rise like differs accordingly. But in our assumption, like in this expression, like we have not assumed, I guess, we have not taken into consideration the surface roughness, but just like if you recall in the class, you just did a balance between the surface tension force and the weight of the liquid to get into this expression. But in general, it also depends on surface roughness. So yeah, and I guess this is clear. So now we go to
Hello.
yes, yes, please.
Sir, regarding surface roughness,
Yeah.
Is it friction? Like, are you talking about friction?
Yeah, absolutely, yes.
Okay, sir.
Because the surface, however smooth the surface we may create, it will always have some small protrusions emerging out of its surface. No matter what we do, we cannot achieve 100% smoothness in the surface of the glass. So because of that, because of the manufacturing, I could say, difference in the type of different types of glass or any material that we've used, it will have different friction factor depending on the the size of protrusions coming out of the surface. So then it may also have effect on the capillary rise, but we have not taken into consideration in this expression. But in general, it also depends on that. So just for your knowledge, I mentioned it here, and I guess Professor Chakraborty also mentioned it in the class. So just for recapitulation.
Okay, sir.
Okay, thank you. So I guess that's all from surface tension and capillary rise. So let me just recapitulate a bit from from fluid statics. So yeah. So what do you like? Just what do you mean by fluid statics? Like, why do we study it? Like, how is it important from a fluid mechanics perspective? Could anyone please explain? Fluid statics. What does the name itself suggest? Vishnu, Pradeep, Priyanka, like anyone, please.
There is no external force.
Okay, one by one, please. Yes, Pradeep, go on.
Fluid will be at rest.
Yeah, absolutely correct. Yes, the fluid will be at rest. So, thank you. So, yes, yes. So, Priyanka, I guess Pradeep also answered it correctly that fluid is at rest. So, what changes or what makes this kind of problems different from, say, the fluid is in motion? So, what happens when the fluid is at rest? Like, if you have attended the previous sessions, one of the 3 TAs, I guess all of them might have discussed regarding what happens when the fluid is at rest. So, and also Professor Chakraborty has absolutely discussed it in his lecture. So, what happens when the fluid is at rest? What kind of forces are absent in the case of fluid at rest?
It will be at equilibrium.
What?
Fluid will be at equilibrium. All the forces will be equal to zero. This is acting on the fluid.
No. Yeah, it's not like that, Pradeep. Thank you for trying, but it's not like that. There will be forces acting on fluid, even though it is at rest. So
Only the pressure thing will be activated.
yeah.
Only the pressure thing will be activated because of the height those kind of things.
Yeah, that's correct. But what is different? Like, what is not acting? What makes it different from fluid when the fluid is at motion? What kind of force is absent when the fluid is at rest?
Shear forces.
Yeah, thank you, Priyanka. You're absolutely correct. The shear forces are absent. Since the fluid is at rest, say I guess Professor Chakraborty mentioned this using a diagram of such diagram in the class. So I guess if it is a small fluid element, say these are dimensions, say So in this case, I could write it, there are no shear forces acting on the fluid element because the fluid is at rest. Okay, no shear forces. So in this case, only the pressure and the body forces would act upon the fluid element. Okay, so I guess it was, I'm just writing it for recapitulation. I won't derive the full expression because I guess sir has very finely discussed this in the class and has given proper expression and proper derivation for this kind of problems. So I won't do the complete derivation. I will just skip most of the steps but reach the final expression and tell you something about the final expression. I guess would be helpful for you. So sorry, and I'm just doing this for the in the forces along the x direction. Okay, you can sorry, you can approximate the same for the y and the z direction. That will be completely correct, but for the case of simplicity, I am just doing along the x direction. Okay, so where I guess bx is the body force along x direction. So like following the steps that has been discussed in the class, you find out the forces, all forces acting along the x direction, and you find out that you get the final expression as minus dp by dx plus rho bx is equal to rho ax. Okay, so don't mind that I'm still keeping the rho ax, assuming the fluid is at motion and disregarding the presence of surface forces, but in general, but in keeping in mind the condition of fluid statics, this term will go to 0 and you're only remaining with del p by del x is equal to rho bx. Okay, for fluid statics, but I wanted to focus upon this expression, say equation 1, then it is 2, because this equation has a special name that you will eventually encounter when you go deep within this course. So this is a very special name. So anybody by chance knows what this equation is called? Okay. What?
Euler's equation.
Yeah, thank you Priyanka, this is, you're absolutely correct. This is known as the Euler's equation. It is same as a Navier-Stokes equation, but just removing the shear force terms. Okay, so Navier-Stokes equation without considering the viscosity of the fluid, the equation that comes up is the Euler's equation. So you don't need to emphasize upon it much for now, because you will eventually read it in the fluid dynamics part, but for your knowledge and for your understanding of the course in a better way, I'm just trying to give you the essence of what you're going to eventually learn. So this is known as the Euler's equation. Okay, so thank you. So again, yeah, so we are left with equation 2, which basically gives us pressure given along x direction is equal to the body force into the density density of fluid into the body force along the x direction. Okay, so yeah, so similarly if we consider for other directions, we will eventually obtain del p by del y is equal to rho by and del p by del z is equal to rho bz. So for this is all for Cartesian coordinate system. Okay, Cartesian coordinates. Okay, so like I will just again go a bit fast because these things have already been discussed in the class, but still, because these things are necessary for solving the problems that we'll do in this today's class, so you need to have some basic recapitulations. So yeah, So I guess sir has Professor Chakraborty has mentioned like what this symbol means. So can you please tell what this symbol basically means?
Free surface.
Yeah. Thank you. Absolutely correct. This is known as a free surface. Okay. So yeah. So say we consider case. Say we consider a case like where we want to find the pressure at point. Say this is point 1 and this is point 2, and we want to find the pressure at point 2. Okay, where it is at a depth say h from the free surface. Okay, so say I want to mold my coordinates in such a way that this is along x, this is y, and outside of the screen, perpendicular to screen, is the z direction. So could end up fluid is completely at rest. Okay, say I'm considering container, stationary container, the fluid is kept there, and like I want to find the pressure at pressure at point 2. So what will be the body force along x direction? Can you please tell? Given this is the coordinate system. Given this is the coordinate system, and this is a scenario, fluid at rest. So what will be the body force along the x direction?
Considering only gravitational force, it will be 0 along x and z.
Yeah. Thank you. You're absolutely correct. So as I already mentioned, it is a closed container, say, and the fluid is at rest, So the only body force that will act in this case is the gravitational force. Okay. So given this in mind, so like I guess then del p by del x would be equal to 0, and del p by del y be equal to 0, right? And here this basically means body force per unit volume. So yeah, force per unit volume. So given sorry I'm again sorry del p by del z equal to 0, sorry. Yeah, so this basically means the pressure is only the function of y in this case. Okay, this specific case only pressure is only the function of y. Then we can basically write this equation as dp by dz equal to rho by, and given the direction of our choice, like we are mentioning that the y direction is along the vertically upwards, so the sign convention for this would give us del p by again sorry it is y, and del y is equal to minus rho g. Okay, and if we follow the proper integration rule, say if we, then this will come out to be minus rho g del y. Okay, now if we integrate it, so I have to keep the points correctly. So if we integrate it from point 1 to 2, then minus rho g dy, and again, so if we measure the height h from the surface 1 to point 2, and given the Cartesian coordinate, the sign convention we have choose for the Cartesian coordinate, so h, it will go from 0 at point 1, this is at point 1, to minus h at point 2. So this is understood, right? There's no confusion, I guess, here. Why I have chosen minus h instead of plus h? Because we are going below the surface, vertically downwards, right? And we have chosen assigned our coordinates to be in this fashion. Vertical upwards is a positive y direction. So given this sign convention, we will obtain P2 minus P1 is equal to rho g h. Then pressure at point 2 will be given by P1 plus rho g h. And if we consider that pressure at point 1 is equal to the atmospheric pressure, then pressure at point 2 would basically be equal to P ATM plus rho g h. So this is a very important expression just to find the pressure at a point given that the fluid is at rest. So I guess this is also clear, and so only thing that remains is the principle of manometry in our for today's class. So the principle of manometry, or the basic principle upon which manometers function, is basically upon this fluid statics, okay, the hydrostatic law. So it is just the application of this expression, okay, the application of this expression, choosing the proper point of reference, like choosing a convenient point of reference. We just balance the pressure at different points and find the pressure that acts at two different points, the difference of pressure between 2 points. So I'll just show you with the help of a diagram so it's completely clear. So say we have a pipe of this form, okay. I guess the same example Professor Chakraborty has used in his class, so I will just follow that only for ease of understanding and also proper recapitulation, because these are very fundamental concepts, and these are what we need to be absolutely clear, so that we can build upon our foundation upon them, build upon our concepts with these foundations. So it's very important for us to be very clear about in these topics, okay. So yeah, I will let's not mention the datum right now, okay. So say this is the center of the pipe, and say we have points 1 and 2, and this is the liquid level that we observe after we have put the manometer in a pipe, and the manometer as a fluid. So I said this the density of the fluid is rho, say, and after I have to mention flow also in this case. There has to be a flow, right? Why do you think that there has to be flow to have this pressure difference between points 1 and 2? Can you please explain?
Could you please repeat the question, sir?
Now I mentioned that there is a flow through this pipe, and then only we have a pressure difference between this point 1 and 2. Like, why is it not possible that without a flow also there should be a pressure difference between point 1 and 2? Why there has to be a flow for there to be a pressure difference between 1 and 2? So would you please tell? Like, given there was no flow, would there be a pressure difference between point 1 and 2?
No, it will be equilibrium. If there's no flow, that will be equilibrium.
Yeah. Thank you. So both of you are absolutely correct. So if there's no flow, there's no pressure difference between point 1 and 2 because they are at same level. Okay, I will again clarify it because it may create confusion, but yeah, they are at the same height. So if there is no flow, there is no pressure difference between point 1 and 2. But given that there is a flow in this case, there will be pressure difference because of the loss in the pressure head because of the friction in the pipe, right? So you will eventually learn in the later part of the course what is pressure head, what is pressure drop in a pipe, how is it measured. So there are various expressions using it. Then you will eventually learn the Bernoulli's equation, how it is derived. So in that case, you will know how pressure difference arises due to the flow between 2 points in a pipe at the same height. So it is the flow that creates the pressure difference along 2 points between 2 points in the same height. Okay. So yeah. So
Hello.
yes.
Sir?
Huh.
Regarding the flow which you mentioned, for
Huh.
the flow to happen between 2 points,
Yeah.
the point of consideration is the energy difference, no, sir, as per the Bernoulli's equation.
Yeah, you are absolutely correct. Yeah, it is the
So
yes. Say.
there can be pressure difference, but energy can be same. Can't it be like that? I mean, since energy is same, there can't be flow, but pressure difference will be there. Can it happen like that?
Okay, you are saying the energy is same, but there is pressure difference.
Yes, can it happen like that? So there is no flow because energy is same.
Let me think about it. Okay, I will just try to write the equation and let's discuss together. Say there are 2 points and there is I am writing the Bernoulli's equation for these 2 points. Say plus z2. Okay, so you are telling that the energy is same and there is no flow. You're speaking like that, right?
Yes, sir.
Yes, but the very principle upon which the Bernoulli's equation is derived is the conservation of energy. So energy is conserved in between these 2 points. Okay, it is by that principle only we have derived the Bernoulli's equation. Okay, so what you have mentioned that there is no pressure drop between the 2 points. Okay, so let me assume that there is no pressure drop between these 2 points, right? So the kinetic energy at both the points are equal. Okay, so yeah, so this is your case, right? This is what you're mentioning, right?
No, sir. I mentioned that pressure difference is there. Can it be possible, like such scenario? Energy is same, pressure difference is there.
Yeah, energy has to be same between the 2 points, right? There is no difference. The energy has to be conserved, right? It is the basis by which we have derived the Bernoulli's equation, right?
No, sir. But for flow to happen, there should be difference in energy, right?
No, that's not the case. No. Have you is it mentioned like that in the lectures, or like is it you are asking out of curiosity?
In general,
Actually, we need
Hello, yes, Pradeep.
we need pressure difference for flow to happen, right? It's not about energy, right?
Yes, that only I'm speaking.
The
They
fluid
have,
should
yeah,
okay.
yeah, that only. So that only I'm trying to explain it to Priyanka. See, the we derive listen carefully. Okay, so we derive Bernoulli's equation with the principle that the energy between the 2 points are equal. That's why there's an equal sign, right? We have equated the energy between 2 points, and this is basically the flow energy. Say En. This is the kinetic energy. This is the potential energy. Okay, so equated these energies at 2 different points, and to actuate the flow these parameters balance each other in a different way. Say we have say in this pipe. Okay, since the area of cross section at these 2 points are same, right? right? So the velocity at these 2 points would be equal, right? If I'm not wrong.
Yes.
Yes, so these are equal, right? These are equal. So the only way we could actuate a flow is by two means, okay? Either you have pressure difference at this, at either P2 is not equal to P1, okay, this is first scenario, or Z1 is not equal to Z2. Okay, say Z1 is equal to Z2. Okay, say there's a case when Z1 equal to Z2. The pipe is placed horizontally. Okay, so the only way the flow could occur is how? If pressure at point 2 is less than pressure at point 1. It is then only the flow could occur, right?
Yes, sir.
Yes. Or there's a different scenario. Say you have no pressure gradient. You are just say like you just kept a tube. You know, I guess you have seen like this. I will explain where. You have a tube like this, filled with water. Okay. And you have atmospheric pressure, or the pressure is same at both ends. Okay. P1, P2, and P1 equal to P2. And the cross section area is same, so there is no point of having velocity difference. So the only thing that could actuate the flow is if we tilt this channel, if we tilt this container in a way that the potential energy at point 1 is higher than potential energy at point 2, right? It is only at this scenario the flow could occur.
Yes, sir.
So yeah, so this is how like the flow occurs. Okay, so energy is conserved, but to actuate the flow you need to have difference in the parameters. Okay, and in general for pipe flow you must remember that pipe flows are pressure driven flows. Okay, why do I say so? See, for pipe flows in general, if you observe carefully, they are of same cross section, right? There is a uniform cross section throughout most of their length. Like if you go in any process industry, you will observe that, or any refinery, you will observe that the pipe that carries the fluid is of similar dimension for a like throughout its length. Okay, so there is no velocity difference between 2 points. Point 1 and point 2. There is no velocity difference because the cross section area is same. Again, like you may observe that the pipe is usually placed horizontally throughout its length, but still flow occurs. So what actuates the flow? What actually actuates the flow? Okay, what creates the flow? It is the pressure difference, right? The pressure difference between point 1 and point 2.
Yes, sir.
So is that clear?
Yes, sir. Clear, sir. Thank you, sir.
Okay, sure. So yeah, so we were here. Yeah, so we are discussing about this. So say the difference between the height of these two fluids is given by delta H. Okay, so 3, and say this is, oh sorry, not this, say this is 4. Okay, so to measure the so to obtain the pressure difference between 2 points, what we basically do is we basically balance the pressure with respect to a particular datum. Okay, and datum is like just a point of reference. Okay, So in this case, we choose our datum to be of this form. Say the datum passes through point 3 and 4. Okay, so this is our datum. Okay, and it is upon this only we will measure our all pressures. Okay, we will equate our pressures. So basically this means that pressure at point 3, because the fluid flow is stationary at this region, so pressure at point 3 would be equal to pressure at point 4. So am I correct? I guess
Yes, sir.
yes, it is correct. Thank you. So this would be, say it is Z1. Okay, the level of the liquid from the point 1, and from point 2 to the surface of the liquid is, say, Z2. Okay, so we just do the pressure balance. So here it is 0.1, so P1 plus, so what is the, say this is some fluid, say this is water. Okay, for ease of convenience, this is water. Okay, so what will be the pressure due to the water at point 3? Because of this height, this, say this height of liquid, this height of water, what will be the pressure at point 3? Yeah, thank you, Pradeep. It will be rho water G into Z1. Sorry, Z1. Okay, again for point 2 this is a bit tricky. Then so up to Z2 the height would be equal to rho water G Z2, but at here, say this is 0.5. So 0.5 to 0.4 the liquid changes. Okay, so we need to take into consideration the difference in liquid along the height. Okay, so it is not same. Let's see here, throughout Z1 the liquid was same, it was a water. Okay, is it because of it is that's why we have directly written it's rho W G H1. Okay, but here since the liquid changes, we need to write the equation separately for a height from 0.5 to 0.4. So it will be basically equal to rho, I guess I should name it F to be easier, rho F G, and 0.5 to 0.4 the height difference is given by delta H. Okay, so if you want to find, say, P1 minus P2, like as you already know, since flow is occurring from point 1 to point 2, so pressure at point 1 is higher than pressure at point 2, so this will basically be again rho water G Z2 minus Z1 plus rho F G delta H. But if you look at this diagram, Z1 minus Z2 is equal to, could anyone please tell what is Z1 minus Z2 here?
Delta H.
Yeah, thank you, both of you. So it is equal to delta H. Okay, so we can then write it as G is common, delta H is common, so it's basically rho W minus rho F. So okay, so this is all about the principle of manometry. So yeah, I guess I have covered, like, just recapitulated all the topics that have been discussed for week 3. So I guess I will directly go to the problems for this week. So yeah, okay, so both of you are there, so please help me out in solving these problems. Okay, I guess you are very clear and like more like better than me in solving this problem, so please help me out. So yeah, I'll read the first question. A block of weight W slides down an inclined pail while lubricated by a thin film of oil as shown in the figure. Yeah, this is the oil. Okay, thin film of oil. The film contact area is A, and its thickness is h. Okay, thickness is h. So this is basically equal to h. Assume a linear velocity profile in the film. The terminal or zero axis velocity v of the block is given by, so these are the options. So yeah, please go ahead and try, and then once you get the answer, just don't tell me the option, also tell me how you approach to solve it, and like we will try to solve it, help me to solve it. Okay, like what if you try for once and just tell me what is the answer and then help me out to solve it. Just look at the options and tell me, solve it and just tell me what would be the right answer.
Hello, sir.
Yeah.
So using balance of forces.
Yeah.
Option
B. Okay, this is one answer. So Pradeep, you feel the same way?
Yes.
Okay, then I think I would not have to solve any this entirely, but just to tell the steps, like for reference. If we tell me, okay, if I'm wrong in any way, just tell me. So weight will act vertically downwards. So we have different components of weight. We dissociate the weight in different components. Say, so this would be W cos theta. This would be W sin theta, right? So this would be the motion of this weight will be resisted by the shear force, right? That acts against the direction of motion of this block. So that will be given by tau into A, right? I guess the area is also mentioned A. So it basically will be equal to W sin theta is equal to tau into A. And how so tau is given by mu del u by del y. Given we have chosen our coordinate systems like this. Okay, you have to mention the coordinate system. Like if you don't mention, that's fine, but it is a good practice to mention your coordinate system once you try to solve the problem. It shows like how clear you are regarding your concepts. So it's very good practice to mention your coordinate systems. Okay, so what is del u by del y?
V by h.
Yeah, they've asked us to choose a linear velocity profile, and if you attended like previous week's session, I've explicitly told that even if they have not mentioned a linear velocity profile, and if the question says that film thickness is very small, we can assume a linear velocity profile in this case. So but here they have explicitly mentioned a linear velocity profile, so it's very simple for us. So it's mu v by h a. Okay, and just play with the terms. So we obtain the velocity as sine theta. So I guess you're right. So let's go into the next question. Okay, thank you for helping me to solve the problem. Let's go to question number 2. A vertical concentric annulus. So both of you know annulus, what annulus means?
Two concentric cylinder tube.
Yeah. Thank you. You're absolutely right. So annulus is basically the gap between the two cylinders. So concentric annulus with outer radius RO and inner radius RI is lowered into a fluid of density rho, surface tension sigma, and contact angle theta, which is less than 90 degree. Okay, so the capillary rise in the annular gap, if the gap is very narrow, is given by, so these are the options. So it's very simple. Again, you apply the principle of the capillary rise. Just go to the fundamentals of how the expression of capillary rise was obtained. Play with the terms a bit and you will very easily get the expression. So please both of you try a bit. I have told you how to approach it. Just tell me what is the answer, and I'll just wait for a few moments. Please try it and just tell me the answer.
Option right A, right?
Yeah? What is it?
Option A.
Option A.
Yes.
Okay. Let's see. So, Priyanka, do you feel the same way? Is it option A? I'll wait for a bit. Or to also reply, and then let's see.
Yes, sir, option A.
Option A. Okay. How do you do it? Could you please tell me? Like, what were your expressions? What were your steps? Please tell me. Like, it's very good practice to let adults also know. So, Priyanka could go ahead. Just help me out. Yeah.
Sir, equating the pressure with the surface tension force.
Pressure.
Yes.
Could you
That
please?
is rho GH to surface tension.
Okay,
force.
just tell me your steps, expressions. I will write accordingly. And let's see. Okay, tell me.
So for surface tension force, it will be 2 sigma by r.
2 sigma by r. Which r? There are two r's now, no? R-O, R-I. Which one? I will help you out a bit. Wait. Basically, this is a tube of this shape, and there is a capillary rise in this region. Okay, in the annulus region, the gap between the two cylinders or tubes, that as you have correctly mentioned. This is Ri, and sorry again, I'm sorry. This is not Ri. This is actually Di actually. So this is Ri and this is Ro. Okay, so this is the problem. There is a capillary liquid rises in the annular region, the gap between the two cylinders. Okay, in these regions. So this is how you have approached it, Priyanka.
Yes, sir.
Okay, so which R have to choose? You have mentioned 2 sigma by R, so which R? There are two radius now, right? Which R?
So surface tension will act at the outer end and at the inner end. So we should take into consider both R's in that case.
Okay, so it will be 2 sigma Ro by Ri. This is what you're telling, right?
Yes, sir. 2 sigma cos theta by Ro plus Ri.
Okay, so it is then is equal to
The pressure difference.
what is the pressure difference? Tell me. I don't know.
Rho GH, sir.
Rho GH. And then you tell that H is equal to 2 sigma cos theta rho G Ro plus Ri. This is what you're telling, right? This is how you approach Pradeep. Is it the same way?
Yes. Actually, I have taken delta P into rho GH. I have equated this.
Okay. So, uh, okay. Let's wait for a while. Okay. Thank you. So yeah. So the thing is, as I've told you, okay, let me be clear. This is not right actually. Option D is the correct answer. This is how I have derived. So let's see if my derivation makes any sense. Okay. What you have tried is also very nice. It's a good way to approach, but unfortunately this is wrong according to what I have derived. But let's see my derivation also, right? So yeah. So instead of equating the pressure, I have equated the forces. Okay. I have assumed this in a way that since this liquid has risen up in this annular region, okay, say it is up to height h. So I have assumed that since the liquid has risen up, there must be a force acting vertically upwards, right? This is basically the force, surface tension force, that holds the weight of this liquid column. Are you getting it? Right? Like, please say yes or no. Like, have you understood what I have tried?
Yes.
Yeah.
Yes.
Yeah. Since there is a liquid column, basically, like if I do the top view of this, say like this, if I do a top view of it, I'm sorry again. If I do a top view of it, the liquid region is basically this part, okay? Again, there is Ri, Ro, right? So, since liquid has risen up to height h, there must be a force that acts in the vertical upward direction to hold this liquid, okay, this column of liquid. And the weight of the liquid acts vertically downwards. That's universal, right? This is very easy to understand. So the weight of the liquid column acts vertically downwards. So to hold this liquid up to a height h, a force Fs must act vertically upward. Okay. So what I do, I equate these forces. So what would be the weight of the liquid column in this case? Could anyone please, both of you please tell, one of you please tell, what will be the weight of the liquid column in this case?
Rho GH.
I said weight, not pressure, weight.
It will be AO minus AI into H. AO minus AI into H.
This is the volume if I'm not wrong.
Into rho. Into G.
Okay. Into rho into G. Yeah, absolutely correct. And that would be equal to the surface tension force. So what will the surface tension force in this case? That is the catch of the problem. Surface tension force. See, sigma is equal to F by L. It's very simple, okay? And L I have mentioned very clearly. It's not the length. It's actually a length of contact of fluid that acts upon the surface of the shape, geometrical shape, that helps to hold its integrity on the surface, right? In the case of a bubble, liquid bubble, that would be equal to the circumference 2 pi r. But again, in the case of a, so it is liquid droplet, but in the case of a liquid bubble, since it has two surfaces, so the point of contact in this case would be 2 pi Ro plus Ri, right? Because the liquid is in contact with both of its circumference of the inner as well as the outer circle, right? So approaching in a similar way for this annulus also. So what would be the surface area, the length of contact in this case?
Two pi Ro plus 2 pi Ri.
Yes, 2 pi Ro. So I just take it common, Ri. Then again I said force, okay? So it will be sigma and cos theta accordingly, like exactly like how Professor Chakraborty mentioned in the class. Okay, the vertically upward component, we need that only, right? So the cos theta component gives us the vertically upward component of the surface tension force. Okay, we cannot see, this is a very important concept for you to know. We cannot dissociate pressure into different components. Why? Could anyone please tell why we cannot dissociate pressure into different components?
Because it is scalar quantity.
Yes, because it's scalar, it doesn't have any component, it only has magnitude. What we can dissociate is a force. We cannot dissociate P into P cos theta and P sin theta. If there is, it's actually, in some cases we do P cos theta into 1, where we take 1 as the area of contact, where P into A gives a force, and it is force that we dissociate. And in the derivation of the capillary rise, we have actually equated the force, the surface tension force, and the weight of the liquid column, and then we have obtained the expression for capillary rise. So I've told you before solving itself that you need to approach in that way, the primary expression that we have used to achieve the capillary rise. So that's why we could dissociate into cos theta and sin theta components. We are not dissociating in the pressure components, but actually the force. Okay, force components. Okay, so yeah, like that. So then approach, then going further, so AO minus A will be given by what? Pi H RO square minus RI square. Please stop me anywhere where you feel like I'm doing wrong. Okay, then RO plus RI sigma cos theta, right? Then just do the cancel out, pi you can cancel out, right? See again, here I can write it as RO plus RI, RO minus RI, right? A square minus B square formula, sigma cos theta. So what we do, we cancel out these two terms. So we need H, right? So H will be given by 2 sigma cos theta RO minus RI rho g. So that would be basically option D. So is it clear?
Yes, sir.
Yes.
Yeah. Okay, see, so again for your recapitulation, see, the expression of 2 sigma cos theta by rho g r is for a special case when your geometry or a tube at which you have measured the capillary rise is a simple cylindrical tube. Okay, in that case only this expression is valid. Okay, but the force balance that we do to obtain this expression is universal. This is a universal law, right? The surface tension force balances the weight of the liquid column. It is by that principle only we are coming to this expression, and that's why that expression, that fundamental expression of equating the forces, is universal. But this special equation that we obtained is for certain geometry, and if the geometry changes, the expression also changes, but the fundamental equation of force balance remains the same. Okay, so whenever you get such questions where the geometry of the problem changes, you need to approach it with the help of the fundamental equations rather than the predefined or pre-obtained expressions for certain geometries. So I guess it's clear. So just keep that in mind, okay, in your future when we are solving some questions, when you encounter some fluid mechanics problems in the future. Okay, so yeah, again question number 3 again is regarding surface tension itself, I guess. Okay, a solid cylindrical needle of diameter d, length L and density rho n may float in a liquid of surface tension sigma. Neglect the buoyancy and assume a contact angle of 0 degree. The maximum diameter d max for which the needle will be able to float in the liquid is. So is the question clear? So I guess it's clear. It's very simple English. It's very simple and
Yes,
clear.
sir.
Yeah, yeah. So please go to the question. Try to obtain the expressions. Take the necessary assumptions to simplify the problem, and then give me the correct option. Okay. So both of you, are you trying? So
Sir,
yeah.
um, like, should we like assume like diameter is smaller than length or?
Yeah, yeah, you can, as you have mentioned, right? You need to take the, you may need to take some assumptions to reach an find expression that matches with these options. So yeah, you may need to take and just tell me the assumption that you have taken.
Sir, if like I took the assumption that length is bigger compared to length of the needle is bigger compared to the diameter of the needle.
Okay, okay.
Getting option 3.
3. Let me see. So I also don't know. Okay. I guess you have chosen option 3. And Pradeep, do you feel the same way? Pradeep? I guess, yeah. Did you get the same answer?
So it's either like 2 or 3 option, I guess.
Oh, okay. It's fine. Either 2 or 3. Okay. It's fine. So, Priyanka, I guess you told the first one. So, could you please tell what you have done to reach an option 3? And option 3 is correct actually. So, that's right. So, can you please tell how you have approached this question?
So, weight of the like buoyancy force is not there.
Yeah,
so
yeah.
only forces is weight of the needle and the surface tension force.
Yeah. So, what is the weight of a needle?
It is density of needle into pi d square by 4 into L into G.
And the surface tension force?
It is equal to sigma into 2L plus 2D.
Oh, sorry again. It is 2L plus 2D. Yeah. Then
I considered that length is larger than diameter, so neglected the 2D.
okay, very nice. So Pradeep, did you approach in the similar fashion? Pradeep?
No, actually it's not.
Okay. So yeah, so we can then cancel out the length, and what are we asked to find? Diameter, maximum diameter, right? So d square will be equal to 8 sigma by pi rho n g, and d max would be equal to 8 sigma, square root of 8 sigma pi rho n g. So yeah, so see, if we would have taken 2D also, then this problem, like, we will get a solution. Obviously we may get an equation, a quadratic equation, then we may need to solve it. Okay, but if you observe in a way that you are given some options and you can take certain assumptions to simplify the problem, and also it is told that it is a cylindrical needle, using just simple common sense also, like, diameter of a needle is absolutely negligible compared to its length, right? If you think in that way, and considering that assumption, you can neglect the diameter of the, since L is much greater than D, you can neglect the diameter of the needle and then find the surface tension force. Okay, but see, again, you have not neglected the diameter in this case, right? It's absolutely logical because it is multiplication, and in this case it's addition. The order of the length is much greater than the order of the diameter. So in this case, the order of L plus order of D would be equivalent to order of L. Okay, but order of L into order of D is not proportional to order of L. Okay, this is a fundamental concept. It's very fundamental, the order of magnitude analysis, that both of you will eventually learn when, if you read the boundary layer theory. I don't think this is in the current course, but whenever you read the boundary layer theory, you will understand the importance of order of magnitude. Okay, so given that thing, you can approach in this fashion. Given this assumption, we reach this expression. Okay, so it's clear, both Pradeep and Priyanka?
Yes, sir.
Yeah, thank you. Pradeep, is that fine?
Yes.
Okay, thank you. Okay, let's go to the next question. I guess it's question number 4, and it is an interesting problem. Yeah, this is a very interesting problem. So yeah, the rotating cylinder viscometer shears the fluid in a narrow clearance delta R as shown in the figure below. Okay, the length of the solid cylinder is equal to its diameter, that is basically L equal to 2R. Okay, assuming a linear velocity again they have given, and see there's a pattern in this case, right? Given that this delta R is much less than R, then in this case only they have assumed the linear velocity profile. They are also very smart. An expression for the fluid viscosity mu in terms of driving torque M is given by this expression. Okay, let me just box it because this is what we need to handle for many questions now, where N, M and K are real numbers. Okay, so the value, we need to find the value of K neglecting the bottom friction. That for the first question we need to neglect the friction at the bottom surface of this, say this geometry. Okay, so basically what they've told is that they have a rotating shaft. Okay, rotating shaft in a cylindrical container. I'm just trying to do a 3D view of the question, so like both of you understand it in a better way. And it is told that this is rotating with an angular velocity omega. So see, and there is a fluid surrounding this liquid, okay, surrounding this shaft. I guess a similar problem has been discussed by Professor Chakraborty in his lectures, so you may refer to that or just recapitulate those concepts. So see, since there is and in these cases it is generally a very viscous fluid for these applications, so that is used to lubricate the rotation of this shaft. Otherwise the confinement where the shaft itself may wear out because of friction. Okay, so they are told that to rotate in this viscous fluid we need to apply an external torque on the shaft. So we need to find an expression for the viscosity given that the external torque to rotate this shaft is given by M. Okay, so the unknown parameter in this case is mu, viscosity. So yeah, I guess you understood the problem. So is that clear, or like I need to repeat it again? Is that clear, Pradeep and Priyanka?
Yes, sir.
Yeah, thank you. So it's a very involving problem, I must say. It's a very interesting and involving problem, and there are many sub questions to this problem. Okay, so you need to derive the expression itself from the start. Like if you refer to the notes, follow the similar steps, find an expression of for M for mu with respect to the applied torque and other flow parameters and flow and geometric parameters, and then we will find out what are the values of these indices and the constant K. Okay, indices and M and the constant K. Okay, so just find an expression by deriving the governing equations as done by Professor Chakraborty. Go to your notes and tell me what would be the value of K for the first question, neglecting the friction at the bottom surface. Okay, so yeah, please try, and like once you obtain the solution you need to help me out to solve the problem also, because I don't know how to approach it. So yeah, please go ahead, take your time. It's an involving question, so please. Okay, sorry to interrupt both of you. I just want to clarify one more concept before like going forward. So Priyanka, could you please pay attention for a while, both of you actually?
Yes, sir.
Yeah, So previously you have asked question regarding your energy head, right?
Yes, sir.
Yeah. So I just gone through my own notes and just try to recapitulate. So you were right. Okay. Uh, this expression that has been, I was also right in some sense that this Bernoulli equation has been what to say, derived keeping in mind the energy conservation. Okay, but in this expression is incomplete in a practical sense, in a way that there is always a head loss in the flow when flow flows from point 1 to point 2. Okay, you know head loss occurs because of friction within the pipe, right? No pipe is smooth enough to have zero friction, and that basically occurs because of what? The viscosity of the fluid, right? If you recall.
Yes, sir.
Yeah, so there has to be a head loss because of the viscous nature of the fluid, right? So given that, even though, like, if you have scenario, say in a straight pipe, say in a horizontally placed pipe, say point 1 and point 2, so v1 will be equal to v2. Why? Because the dimensions are same, right? Again,
Yes.
z1 equal to z2, and you are saying that there is a flow because of pressure difference, say p1 is greater than p2. But to satisfy this equation, there has to be a term on the left hand side, right hand side, to balance this pressure difference, right? The difference in the pressure head. So that is being balanced by this loss term, okay? The head loss term in the equation. So is it clear now? The energy is conserved, but the difference in the pressures are being balanced by a head loss term, this term.
Okay, sir.
Okay, I guess it's clear now. So yeah, please proceed with the given problem. So thank you again asking such doubts. It's very important for me and as well as the students. More importantly, me, for to make my concepts clearer. So thank you, and please go ahead with this problem. Uh, okay, then what I would do is I will stop screen sharing for a while and try to derive the expression myself. Then after, say, 4 minutes, say 4 or 5 minutes, I will again share the screen and compare both of our expressions, okay, and see how both of you have approached. Okay, is that fine?
Yes, sir.
Yeah. So yeah, I will just stop sharing for a while, and then we can again discuss after both of you have reached the final expression. That would be very good, I guess. So yeah. Okay, then I'll wait for 2 more minutes. Then I'll share the screen again and discuss the answers. So yeah.
Hello, sir.
Yeah. Have you?
So for first one,
Yeah, please. First one, yes.
the answer K is 4.
Okay, let me check. Okay. Just share screen. Start broadcast. Okay, let me check. Okay. Okay. So yeah. So for the first one, you're saying answer is 4.
Yes, sir.
4. Okay. What is K?
Second one,
Okay. Wait. Let's wait. Okay. So what is the expression that you have got for mu? Could you please tell? Mu is equal to
M
m
delta R
delta r
by
by
4 pi
4 pi.
divided by
Yes.
omega R power 4.
Capital R, small r
Capital R.
to the power 4. Okay. So yeah, this seems correct. So let's wait. Pradeep, have you obtained the same expression? Pradeep. I guess he's also doing now, so that's fine. Still doing, so that's fine. Yeah, you're correct. So comparing these expressions, so we find the value of k to be equal to 4. Okay, very nice, thank you. So question number 5, I guess. So we need to find the value of k including the bottom friction now. Okay, now we cannot neglect the bottom friction, we need to include the bottom friction. So keeping that in mind, have you done it, or like do you need a bit more time to obtain that?
9 by 2.
9 by 2. Okay, let me check.
Yes, sir.
I don't know. Okay, so could you please tell how have you done it? Just tell me the steps. I don't need the full expression. Just tell me the steps.
For the bottom case, I did integration, sir.
Okay, so you have integration in the sense, like, please elaborate a bit more, like what have you assumed? Say, let me draw it. That will be good. So, or let me just share what I was trying to do. So yeah. So yeah, Pradeep, you want to say something?
No.
Okay, that's fine. Feel free to speak up, okay, if you have any doubt or you're just stuck somewhere. So
Okay.
sure. This is the fluid. So now there is a friction in the bottom part also. Say omega. Say, okay. So how did you evaluate the friction in the bottom part? say again I assume a circular cross section. If I view from the top, it is very bad actually, so let's draw it nicely. Yeah. And then yeah, please tell me then, how have you assumed, how have you done the integration, or which elemental surface that you have taken? Please tell everybody, so that will be good.
Sir, I took a ring shape, sir, at distance r.
Okay, so a ring shaped elemental area at a distance r from the center of the cylinder. Yeah. And then now
Then I applied the Newton's law of viscosity.
yeah,
for this one.
yeah, tell me the steps.
For this one, velocity is that r into omega. And the gap is delta r. So
Okay, gap is
and
delta.
area is 2 pi r into dr.
dA is 2 pi r dr, yeah, the area of the elemental ring. Right.
Yes, sir.
And then how will you calculate the moment?
Then for the torque,
Yeah.
Torque is nothing but force into radius.
Okay. Yeah.
Force is given by stress into area.
Okay. Stress into area. Yeah.
And stress we get from the viscosity, mu into V by delta R, because it is linear profile.
Okay. Like that. And then again there is an area 2 pi r dr. Then again there is a radius, right? So I guess this is an elemental moment instead of the complete moment, so I need to mention it. And this is a not the complete area but the elemental area, so if I'm not wrong. So yeah, so you, I guess, basically integrate these expressions. So it would be, what are the constants? Mu, sigma, delta r, 2 pi are constants. We integrate r cube dr, right?
Yes, sir.
Yeah, then I guess if we integrate it, we will obtain an expression like, what is the expression that you obtained? Tell me the final expression.
T is equal to, M is equal to pi mu
Wait,
omega
pi mu omega,
r power 4, capital R power 4,
yeah,
by 2 delta R.
yeah. And since you're taking to find the complete force, complete torque, you need to take into consideration the friction at both the lateral surface area and the bottom surface. So what you have done?
So I added the 2, sir.
Okay, so m net, say the net torque is equal to m1 plus m2. Say this is m2, and you initially you have obtained this is m1, say. So you add both of them, mu sigma 4 pi r to the power 4 divided by delta r plus pi sigma r to the power 4 mu divided by 2 delta r. So what are the common here? It is mu is common, pi, sigma, r to the power is also common, and delta is also common, I guess. Then we are left with 4 plus 1 by 2, if I'm not wrong. Then you get mu pi sigma r to the power 4 by delta r and 9 by 2. So this is the net torque if we consider the bottom surface also. So if we isolate mu, then we can write it as m delta r 9 by 2 pi sigma r to the power 4, right? And if we compare it to what is the final expression again? Mu is equal to m delta r 9 by 2 pi sigma r to the power 4. I guess I'm right. So yeah, so if we compare it to the expression, mu equal to m delta r to the power n k pi sigma r to the power m. So here I guess if you compare both expressions, then k is equal to 9 by 2. So Pradeep, is that clear?
Yes, sir.
Okay, so let's look into the next question. What is the value of n? And it's very simple now, I guess. So what is n then? Compare about the expressions. 1. Yeah, absolutely correct. And what is the value of m? M.
4.
Yeah. Thank you. So yeah, this was very involving question. I guess you had to derive it from the start, and if you have followed Professor Chakraborty's lectures, you would easily derive it. But it's very important. Okay. So yeah, the next question. It's a very trivial question, but let's see. What is the pressure within a spherical water droplet of diameter d if the atmospheric pressure outside is P0? The surface tension coefficient of water in air is denoted by sigma. So it's a very trivial question, but still you have to think little bit and recall the expressions for spherical droplet, the surface tension for spherical force for spherical droplet. So what is the expression? Recall the expressions and just tell me what's the correct option. Pradeep, Priyanka, yeah, please.
Sir, option B.
B. Okay.
B, second one.
Yeah, this one. So, Pradeep, do you feel the same way? Yeah, Pradeep, do you feel the same way?
No, I'm checking that.
Okay, sure, please take your time. Okay, like if Pradeep doesn't mind, like we are now short of time. We had 2 more questions to go, but so I'll just tell the answer. Like Pradeep can continue to find that's fine if you don't mind. So I would like to proceed. So the answer is B. Okay, it's very simple. If you recall your previous like expressions for the surface tension, that when sir has discussed about surface tension, he has explicitly mentioned about various expression for the surface tension in different cases. For spherical water droplet, it was 4 sigma by d. So you may just question like why there is an additional pressure term. So could you please anyone tell? Priyanka, can you tell like why there is an additional P naught term here now?
So this 4 sigma by D is a difference in the pressure.
Yeah, thank you. It's absolutely correct. So we basically express the difference in pressure. We assume that the outside pressure is atmospheric pressure. So the additional pressure the additional pressure force that is required by the bubble. The additional pressure force that is within the bubble that has been balanced by the surface tension force is what given by 4 sigma by d. Okay, the additional pressure force. That's why it is P naught plus 4 sigma by d. But we just tell the excess pressure that is required, that is being balanced by the surface tension force, is given by 4 sigma by d. It is the excess pressure. That's why we don't explicitly mention usually P0 by d, but it's actually P0, the atmospheric pressure, plus the excess pressure. Okay. Okay, so yeah, so the final question for today's class, or today's session, I must say, not class, today's session. So yeah, so this is basically the application of the manometry principle. So I will just zoom a bit, I guess. Yeah, it is clear now. So yeah, please, it's a very simple question, but again you need to apply all the basic steps, choose the correct datum, and then find the the respective heights. So please go ahead. Every information is given in a diagram in the question itself. Sg is the specific gravity of Mercury is 13.5. Neglect the air density. So everything is given. You need to find H1 and H2. Subsequently H2 for the next part. So yeah, please, it's very simple. 2 or 3 lines of equations. Yeah, please. So okay, let me also try to solve like accordingly, and you can help me out. I will just write the expressions, then you may tell me what I have chosen as the,
Centimeter.
yeah, what you have done?
H1 is 6 centimeter.
6.
Yes, sir.
Okay, and H2. Okay, you can evaluate. Pradeep, did you also get 6? Yeah, I couldn't get the answer. Have you also got 6, Pradeep? H1 equal to 6. So yeah, if we choose the datum to be here, then we get this height as 8 minus H1. Then we basically do the pressure variance above this datum line, so it will basically equal to 27. This is the height. Rho water into G would be equal to rho Hg, not write G, then you may get confused, 8 minus H1 G. So you cancel out the acceleration due to gravity, then this 27 rho W would be equal to rho Hg into 8 minus rho Hg into H1. Then we just divide, then we take H1 would be equal to 27 rho W by rho Hg. Oh no, I'm sorry, be equal to, just reverse, 8 rho Hg by rho Hg minus 27 rho W by rho Hg. I just took this term this side, this term in the LHS and just that in RHS. So then we get H1 is equal to Priyanka can go ahead with the next question, H2. So yeah, this is basically 8 minus 27, and since it is 13.5, because rho Hg by rho water will be equal to 13.5. okay, then it basically becomes 8 minus 2, because 13.5 into 2 is 27. This is given by 6 centimeter. So this is simple. So you can apply the similar principle in the other side also. Choose the lower one as a datum. So Priyanka, did you get the answer for the next part?
So 52 centimeter.
Yeah, absolutely correct. So following the similar steps, you get the answer to be 52 centimeters. So I guess time's up for today. So Pradeep, did you obtain the answers? Pradeep.
Yeah, hello.
Yeah, please. Did you obtain the similar answers?
First one I got it. As for second one, you take it for both densities, right? So,
Yeah, just compare with mercury and the oil
okay.
and choose the datum as I mentioned. It makes the problem simpler. You don't need to consider water then. I guess there's no water. You just need to. Why is this? You just need to compare the two heights. So I guess that's very simple now. Okay, I will just go do it along with you. So it will be very easy. So above this datum, if you go, then it basically becomes, say, rho oil H2 into G, right? And this height would be 8 minus 5 equal to 3, right? So it will be equal to rho Hg 3 into G. G you can cancel out. H2 would be basically equal to rho Hg by rho oil into 3. So if you do the calculation, then just compare the specific gravities. 13.5 by 0.78 into 3. So if we do the calculation, it will come around 51.92 actually. So you can just take it as 52, what is given in the option. So yeah, so I guess we are out of time today. So thank you for joining. I also encourage you to join other classes, other sessions for the same course to get better understanding of the concepts, and obviously attend the lectures by Professor Chakraborty. He is the best one among all of us, and he is the one who will teach you in the best way possible. So yeah, so thank you again both Pradeep and Priyanka and for joining the session. So yeah, meet you next Sunday. Okay.
Thank you, sir.
Thank you so much. Okay.
Thank you.
Thank you, Pradeep. Thank you.